So folks, in this video we're going to give an overview of working with inverse functions. So I want to sort of guide our process with a nice little illustration here. So in certain cases, like this particular function that I'm giving you here, where maybe the input values a, b, and c, maybe they get mapped to these output values 1, 2, and 3 by maybe a goes to 1, b goes to 3, c goes to 2. So if this is a function f here, what we'd like to do is remind ourselves that this is the domain set. These are the independent variables, and they get paired with unique dependent variables over here. So this is the range set for our particular function. Well, when we go to construct an inverse function, we're going to make the function, this inverse function, which we'll denote with f, we'll put a -1 in there, that's for inverse. It's going to take the range values from the previous function and treat them as if they were now domain values. And it's going to then map them to range values, which were the domain values of the original function. So it's going to map them to a, b, and c. And specifically, we will map them in such a way that we just undo it. So previously, for the function f, the domain value a got mapped to the range value 1. So under f inverse, the domain value 1 needs to get mapped to the range value a. Likewise, the domain value b got mapped to 3 under the original function. So under the inverse, 3 has to get mapped to b. Likewise, the domain value c got mapped to 2, and so under the inverse, the domain value 2 gets mapped to c. So that's the basic idea. Now, something that I've glossed over is that we can only do this procedure that I've just shown you if our function is something that we're going to call one-to-one. I'll define that below here. So we will not always, this is important folks, we will not always be able to construct inverse functions. So we can only construct inverse functions of functions provided they are one-to-one. What do we mean by one-to-one? Well, a function is said to be 1 to 1. And you'll often see, I don't know if this is, everybody does this, you'll often see me just write 1-1 for one-to-one. If for every, if whenever f of x1 equals f of x2, that implies x1 equals x2 for all x1, x2 in the domain. Folks, that's the correct definition. That's a little bit difficult for some students to suss out, so I've got a better way of saying that. In simpler terms, a function is said to be one-to-one if different inputs always yield different outputs, i.e. two different domain values always have two different range values. So let's go ahead and look at three functions that are not one-to-one. The first one that maybe we could look at is the function f of x is equal to the absolute value of x. If we were to look at the graph of f of x equals absolute value of x, this is one of our library functions. Hopefully you've seen it before. If you haven't, we'll review it again later on in the semester. But here's the graph of the absolute value function. And I want to point out that if we were to take 1 and take its absolute value, the absolute value of 1 is 1. So we've got this ordered pair right here, 1, 1. The absolute value of 1 was 1. But if we were to take -1 and plug it into the absolute value function, the absolute value of -1 is also 1. And here we see that this function is not one-to-one because here I have two different domain values. So we've got the domain value -1, the domain value 1, two different domain values, but notice they both have the same range value. And that's one instance, and in fact there are actually many, many instances for which this function fails to be one-to-one. So the next function that I want to look at is maybe this function right here, g of x, and g of x is the function x cubed minus x squared minus 4x minus 4. And I think it would be a little mean to expect you to graph this function. I think this is a slightly difficult one to graph right off the bat. But it turns out that if you were to graph this function, the graph of this function looks like this. We go -1, -2, 1, 2. If I were to sketch the graph of this function g of x here, its graph, let's see here, it has zeros at -2 and at 1 and at 2. You don't know this, folks. Just bear with me here. I sketched this on my own before this lecture. And the graph of this function would look something like this. And I realize I have a typo here, folks. This should be a +4. Okay. So here I've got the graph of this function. I want to notice that, for example, if I look at the zeros here we've got 2, 0, and here we've got 1, 0, and here we have -2, 0. So there are 3 different domain values. They are -2, 1, and 2 that all give the same output of 0. So this function is not one-to-one. And you can see that there's actually many other places where this function is not one-to-one. So for example, if I were to pick maybe this range value right here, you can see that there are 3 points on this graph that all have the exact same range value. All 3 of those domain values, here, here, and here, would give the same range value as this. So we're not one-to-one. Notice that, and let me, I'll just extend this just a little bit further up here. Notice that this function is sometimes one-to-one. So for example, if I were to look at, say, this range value right here, there's only 1 point on the graph that has that particular range value. So it is one-to-one in some places, but it's not one-to-one everywhere. Folks, the last one I want to look at is just our standard quadratic x squared. And let's look at that here. If we were to look at the graph of f of x equals x squared, or g of x equals x squared, let's sketch that standard quadratic. Let's see here, we did f, g, let's call this h of x equals x squared. So this is not one-to-one, and we can see that because there are many times where different input values will give different output values. Notice there's only one output, there's only one input that outputs 0. So it is one-to-one at 0, but it's not one-to-one everywhere. For example, for this range value right here, there are 2 points which output the same one. Folks, don't let the first and last example cause you to make a misconception. These graphs do not need to be symmetric to be one-to-one, and in fact, this g of x that I sketched here is not a symmetric function, and it's not one-to-one. Okay, let's continue. So now let's go ahead and sketch 3 functions that are one-to-one. So here's a function that's one-to-one, just the function, let's do this right here. This would be maybe the function k of x. It's a line, so maybe it's the graph of k of x equals x plus 2. This linear function here is one-to-one. There are no other input values, say for this this domain value outputs this range value. There is no other input on this function that outputs the same range value. So if this is the order pair, let's say this is 1, that would make this 3. There we have the order pair 1, 3. There is no other point on this graph that has a range value of 3. Why? Because this function is one-to-one. And we could do another one. So we could look at the graph of, say, the exponential function. And I'm putting this up here. We haven't reviewed it formally in this class, but hopefully you've seen it before. If you haven't, that's all right. We'll review it eventually. But this is the graph of L of x equals, say, e to the x. And notice that this function is also one-to-one. And in fact, let me just go ahead and say it now, that the functions that are non-one-to-one, they're going to fail what we call the horizontal line test. So if you're looking at the graph of a function, you can quickly determine whether or not it's one-to-one by checking to see whether it passes the horizontal line test or not. So notice that, and this is going to make things a little cluttered here, so folks, I'll erase it once I do so. But if I were to draw some horizontal lines, that was supposed to be a different color. If I were to draw some, horizontal lines here, notice that these horizontal lines sometimes, not all, like this one didn't, but many times these horizontal lines intersect the graph more than once. And we see that here, here, here. So all 3 of these graphs fail what's called the horizontal line test, the first 3. But you can see that these graphs, if I sketch horizontal lines, these graphs all pass the horizontal line test. So that's where I'm talking about this horizontal line test, which should ring a bell because earlier when you studied functions, you studied something called a vertical line test. Okay. So I want to do one more, and this one's kind of an important example here. And this is going to be the function m of x is equal to x squared. And you should be saying, hey, wait a minute, Charles. In the previous example here, you just said the function x squared is not a one-to-one function. And that's true. That's 100% true. What I'm going to do is I'm going to restrict this to only the part where x is greater than or equal to 0. Because now if I draw the graph of this function with this restricted domain, we see that this graph is now a one-to-one function. That is, it passes the horizontal line test. Whereas this function here, we would say that it fails the horizontal line test. And we'll just leave it at that, folks. Hopefully this gives you kind of a quick overview of what we mean by one-to-one functions. Okay, continuing on. So let's see if we can identify which of the following functions here are one-to-one. We've got a handful to look at. This function is one-to-one. If you were to look at the graph of this function, you would see that the graph passes the horizontal line test. We just learned how to graph these lines the other day. It's got a y-intercept of -5 and a slope of 3, and so the graph of this function looks something like that, and you can see that it passes the horizontal line test. Put another way, if I were to say solve 3x minus 5 equals a for some number a, you will only get at most one solution to that, meaning there aren't two different values of x that will output the same number a for this. That's what it means to be a one-to-one function. Now, we have not looked at the graph of the sine function yet. That's on our docket of things to do for this course, to study the sine function's graph, and we're getting really close to that. It'll be next week. But we haven't graphed the sine function yet. Nonetheless, we should suspect that this function is not one-to-one. So let's assume that this is measured in radians. If I were to ask you to find, say, j of pi over 6, that's asking you to compute the sine of pi over 6. And we're getting a little bit better at computing these. If I were to go ahead and draw my reference triangle for the angle pi over 6, there it is right there. And that ordered pair is the square root of 3 over 2 comma 1/2, and when I want to evaluate the sine function, I want the y-coordinate, and so we would see that that would be equal to 1/2. But if I were to go ahead and find j of 5 pi over 6, well, if I were to sketch the reference triangle for the angle, that's a little bit off, let me fix that, folks. If I were to sketch the reference triangle for the angle 5 pi over 6, that was pi over 6. Then we have this ordered pair. This is minus the square root of 3 over 2, comma, positive 1/2. But again, when I want to evaluate the sine of this particular angle, I want the y-coordinate there. And the y-coordinate is also 1/2. And in fact, there are actually infinitely many answers to this problem. So this is not one-to-one. Now, I'll just show you. We haven't learned the graph of the sine function yet. Don't worry about this now, but I'll just show you if we were to sketch a graph of the sine of x, it would look like so. And it's the graph of the sine of x, and you can see that yes, this graph certainly fails the horizontal line test. We'll look at that in more detail in later sections. Okay, so folks, I'm going to stop this video here. What I'd like you to do is try to answer C, D, E, and F here. And I'm sorry, the order is a little bit off, but C, D, E, and F here. Go ahead and check that. Determine whether or not these functions are one-to-one. And I'll see you in the next video.